We're good. Okay. Thank you. Thank you. All right, go ahead.
Okay, so hello everyone. Unfortunately, some colleagues of mine cannot join, and we do a shared presentation. So my first question is whether Simon and Alex, can you hear us?
Yes, we can hear you. Can you hear us?
Yes, we can. Can you hear us well?
Oh, we can no longer hear them because they're not plugged in. Can you say again?
Oh, hello.
Hello.
Yes, okay, we can hear you. It's a little bit quiet, so we'll have to relay the questions because we have to unplug from the AV system. Okay.
So Alex, then I guess you can start.
Yes, thanks.
Yes. Is it possible to hear for everyone? Not really.
You may have to do the.
Yeah, and then I do the whole presentation and then forward the question.
Try this. The only option. It would have worked beautifully, but not in the slides. Okay. Try again.
Can you hear us
Simon?
well?
Yeah. Is that better? Good. All right. A little higher.
Okay. Sorry.
Okay, good to go. Then let's start. I hope you can hear me well. Welcome to the presentation. So we're from BMW. We're working on the autonomous driving project here. This is a huge project with thousands of people working on it. It's one of the most, well, it is the most complex software project at BMW, and it encompasses everything from your basic parking assistance functionality to full-blown level 3 autonomous driving on the highway. And you can think of it as just a huge, mainly C++ workspace, and the output is a binary which we send to the plants at start of production that gets baked into the new cars, essentially, that runs on the vehicle ECU, the vehicle computer. And our job within all of this is build automation. So essentially, in a nutshell, validating, testing, integrating developer PRs as fast as possible, and nowadays as cost effectively as possible. Nowadays, we're doing a really great job, and developers also give us that feedback, but it hasn't always been that way. It's been quite the journey to get here. The journey over the years has involved a number of transitions, migrations, and we want to highlight just a few of them. There's for sure not an exhaustive list, but just a few to highlight. First, a bit of background. So at BMW, we work in what's called service packs. So you can think of service pack as like a subset of features or subset of functionality, which we release every few years. For example, the 2021 service pack, 20. Okay, someone muted me. I can continue. I hope you can hear me still. So in these service packs, we get a bunch of feature requests or things that will bake into the new cars before the start of production. And before the recent service packs, I hope you can hear me still.
Alex, we can still hear you.
Okay, great. So before the recent service packs, we realized we had to upgrade our tooling quite early on because of the planned increase in complexity and the planned increase in features. And some of the changes we made are as follows. So the one at the top is repo structure. So back in the day, perhaps 6 or 7 years ago, we had hundreds of different repos, 200 plus, and each of those repos had a different build system, CI system, access profile. It was basically impossible to access all of them, or very difficult, actually. And as the increase in complexity happened, the amount of cross-repo or cross-component dependencies also increased, and validating that a change in one repo didn't break another repo became quite difficult. Nowadays, we have a virtual monorepo, so everything all in one repo to a degree, and it's very easy to know, hey, does my change break something, essentially? And of course, we have healthy dependency checks to prevent dependencies getting out of control, but it's much easier to validate your change. Additionally, back then, we were using Jenkins as our CI system. It worked fine, but even back then, we had some scaling issues where it was struggling with our load, and we knew with the planned increase in features and planned increase in complexity, it definitely wouldn't scale. And nowadays, we use Zool, which is great because Zool's flagship feature is cross-repo gating or cross-repo merge queues. So nowadays, we don't have any broken states of the repo anymore. Everything's always green. Additionally, back then, we were using a variety of build systems, primarily CMake, but also SCOMs in quite a few repos. Again, it kind of worked fine, but we had slow local builds and also slow CI builds, with too much being unnecessarily recompiled. And incremental builds was sort of a myth or a dream back then. But nowadays we use Bazel, and Bazel supports incremental builds out of the box, as well as lots of advanced features like sandboxing, hermetic builds, and remote build execution. And it was a good job. We did all of these migrations and tooling changes because our foresight did come to fruition. So the increase in scope and features did lead to drastic increases in a number of areas. Here are some statistics on the table. So you can see things like lines of code in our repo, quadrupled the number of developers working on our project, more than quadrupled the number of computers in the car, ECUs, tenfold. And perhaps relevant for this conference is a CI load. So back then we had around 2,000 to 3,000 vCPUs peak, but nowadays it's more closer to 40,000. And of course, with that, the number of builds per day also increased. So in summary, it was really great that we made the decision to migrate to new tools and sort of future-proof our project, but just switching to new tools is not a silver bullet, of course. It doesn't solve all of your problems immediately. So on top of these tools, we had to think out of the box and innovate and advance our project even more. And to talk about some of those innovations, my colleague can talk about that more.
All right. Hello. So I will give you some insights into 3 of our most successful CI innovations of the past years, starting with incremental builds and caching. So in our CI, we're using actually dynamic build nodes, and these nodes are being destroyed after each build. So we cannot simply reuse results from previous executions on that node. In order to utilize incremental builds, we implemented 2 types of caching mechanisms. First, we use disk images. These images are built once per day. We mainly bake external dependencies in our Git repository into these images just to have a head start. But in order to really benefit from incremental builds, we need a very hot Bazel cache with the most recent intermediate build results. And this is where our remote cache comes into play. The remote cache is a network-based shared cache, and it can be accessed by each build node. Multiple builds can benefit from this shared cache, where intermediate build results from one build can be reused by the next. And most of our builds actually benefit from that caching. But there are some outliers which invalidate the whole cache and thus have to rebuild everything from scratch. And in these cases, our builds would benefit from more hardware resources to speed up their execution. So this leads to our next innovation. In order to speed up those really long-running builds, we introduced remote build execution to our jobs. Remote build execution is a Bazel feature where Bazel distributes work to a whole remote cluster of worker nodes. In contrast to a single machine build, which is bound by its CPU cores, remote execution can scale to almost any number of worker nodes. So if we want to run a job with thousands of parallel workers, we can just do this with a simple Bazel flag. So with remote execution, we can give Bazel all the resources it needs exactly when it needs it. And our CI jobs are not bottlenecked by the hardware resources anymore, but there's still improvements to be done. For example, our dynamic build nodes still need to be prepared before actually starting the Bazel execution. This can cost us up to 20 minutes of runtime just preparation. So we had an idea. Why not reuse the dynamic build node for multiple builds? So when reusing an existing build node, we can skip the whole node preparation and we can benefit from really hot caches on the node because the previous build already rendered for us. And in Zool, these nodes are called meta-static nodes. And this is how it works. First, a backing node is spawned the same way as a regular dynamic node would be. After build execution finished, the node becomes idle, making it available for subsequent node requests. Any subsequent builds can then benefit from a pre-warmed environment and almost instantly start with the Bazel execution. If no idle backing node is available, Zool can simply spawn a new one. And after backing node is idle for too long, it will get cleaned up automatically by Zool. And with metastatic nodes, we get all these nice benefits of long-running CI workers, such as really hot caches, without the downsides of having to maintain the worker nodes. If we register that the node becomes unhealthy, we simply kill it and spawn a new one. So in summary, how much did these innovations actually speed up our build times? So first, as a baseline, when we do a clean uncached build of our software stack, it roughly takes 10 hours on a 32-core build node. Doing the same uncached build using remote build execution, we can get this down to 1 hour. Adding caching to our builds, we get our median runtime down towards 20 minutes. And executing the same cached build with RBE on metastatic nodes, we can get this number down to only 3 minutes. And you can see our innovations of the past years significantly improved the build times. Our system is ever growing and ever evolving. We're building new cars every year, actually. So we need to continue on our journey to improve our CI. So for a glimpse into the future, I will hand over to Max, who will tell you more about it.
So, can everybody hear me when I talk about the microphone? We currently employ various pipelines at different stages in our CI. Each serves a specific purpose. So, for example, the pre-serving pipeline is designed to provide our developers with quick feedback on their pending PRs. On the other hand, our post-serving pipeline is executed after each PR when it is merged into the master branch. And there we run extensive and long-running tests, such as simulations and on-hardware testing. And to maintain an always green mainline, we also use a gate queue, which is also known as a merge queue. And this pipeline stacks pending changes onto each other and tests them in parallel to ensure that all changes are both compatible with the master and also all other pending PRs in the queue. However, we've identified a bottleneck, the gate queue. So due to the long runtime and the sequential nature of it, it has the fewest run over a day. And if we look closer at it, the actual runtime of the pipeline is much longer than compared to the other pipelines. Nearly half of the time is wasted on waiting. So therefore, we want to include machine learning into our continuous integration to optimize our gate queue by first selecting which PRs we enqueue, especially during business hours, to minimize gate resets, so failures in the gate, and increase throughput. We also want to determine the order of execution for the selected PRs, as successful runs prior to the failure can be merged immediately, whereas those following need to be rescheduled. And we also want to batch PRs that are likely to cooperate without any conflicts, and thus saving resources and further increasing throughput. But the challenge lies in the fact that each PR has the potential to fail not just against the mainline, but also against any other PR in the queue. And therefore, we cannot simply evaluate PRs using machine learning in isolation. So, for example, if you look at this pipeline, the PR on the left side introduces a new test, which tests a certain method, and we have in parallel a PR which changes the method being tested. So if you look at isolation, both will pass, but if we enqueue them into our gating system, the other one causes the other to fail. And therefore, to predict build outcomes and apply this optimization, it would seem that we need to test all combinations of pending PRs, and unfortunately that is not feasible, as we have usually hundreds of PRs waiting. And we intend to integrate machine learning with search algorithms to find a suitable solution in a reasonable amount of time. And the goal is to improve our throughput, especially during business hours when developers' activity is at its peak. Well, by adopting this, we hopefully cannot maintain our not only maintain our stable mainline, but also accelerate the overall development process, ensuring that our team can deliver high quality software at a faster pace. So in summary, we talked about our transition from a poly repository structure to a monolithic repository with a shared continuous integration. We elaborated on the optimization we already implemented to help us keep the build times low. And last, we gave an outlook how we want to use machine learning in order to speed up our CI. So thanks for your attention.
One, maybe two questions. Then we have got you. Yes, yeah.
I have a question. So I saw that there was upscaling and downscaling that's automatic, right? Were there teams in BMW that were surprised by the CI build? After, it's like, let me say that they did something, so many changes, and then you upscale, run, and then it's like build them for it. Is that how it works? Or do you might look at your face, probably not.
Yeah.
There were no teams that were surprised because I'm probably you're eating the costs.
I think that Simon or Alex, you can answer that question. Did you hear it? Because like I was not involved.
Could you summarize the question for me? Sorry, I didn't hear it well.
Yeah, so
Finally found how to turn that microphone on, but it was a big mistake. I'm sorry to everybody.
were there teams that were surprised by their build after unbounded upscaling events?
So you say the question was, were the developers surprised by this?
By the upscaling events, yes.
By the build.
By the build.
Okay, no, it's completely transparent to them. Zool decides where to spawn a new build node. Either it's a new backing node, and then you have some of the preparation time, but most of the time is actually on a pre-warmed backing node, thus speeding up the builds.
Most of the time, you run on pre-allocated fleet with expected costs.
I'm sorry, I did not hear it. Sorry, it's really quiet.
Okay, so does it mean that most of the time builds run on pre-allocated fleet? Thus, there are no surprises when it comes to like pre-allocated fleet with expected costs?
No, these nodes are spawned completely dynamic. It's all EC2 instances, and usually, like, our users are used to the dynamic nodes, where each node has to prepare for some time. And with metastatic nodes, we are simply reusing an existing EC2 instance, if you so will, and schedule multiple builds on it. And this makes some of the builds faster, or actually most of the builds faster, because many backing nodes are already running and already warm.